Now we have started. Okay. All right. All right. You also always have a eye on whether this recording has not been started. If the recording is started, the session will show this session is being recorded. Okay. Uh, Jitendra's question is, do we cover NoSQL? In this, no, we do not cover NoSQL in this. But if you are specifically looking out to just understand the basics of NoSQL, I can share a video from our other session. All right, so you can just go through that one, and we will cover the how to connect to NoSQL and get data from there. Great. So no other questions before we start. All right. All right. So we have the other session. Okay. Let me just open I think looks like there were a few more slides which we had to cover in the last session, which we have not yet covered, and also that word count problem which we need to work on today. There are two big hands-on exercises which we will do today. One starting with a word count, all right, and second will be the page rank kind of a problem. And if the time permits, we will go ahead and also do the JSON loader. Okay, we will download the data from the internet regarding the stock prices, load it in Spark, and then we will charm it. All right, if time permits today, we will do that. Otherwise, we'll do that tomorrow. All right, so be ready be ready to do the hands-on at any point of time as well. If you are in a position to start Spark, you should just start. All right. So I mean, you know that you can log into Hadoop 3, Hadoop 1, and then start Spark, right? Great. So we were somewhere near sample. We had talked all about this, right? All right. So we were on this particular point. All right. So we have discussed about various kinds of actions. Actions mean whenever we call an action, it brings data or it does things on the driver node. And also an action causes things for execution, meaning all the RDDs an action depends upon, those RDDs and the transformations due to which those RDDs are being formed, all of those transformations are executed. Okay, I hope there is no doubt about this fact. Okay, So we talked about multiple kinds of actions. We went through this, how is the length being computed, and also if you, in this particular example, we notice that the driver node is also being used for execution. Okay, so if you see, the summation function was first executing on node 1, parallelly node 2, node 3, and once all the nodes have given the length, right here it has given 24, it has given 14, and again 24. These values are gathered on the driver node 24, 14, and 24. These are the line lengths which we talked about. We were trying to compute the line lengths of various strings. And then the same process what has happened on individual node, okay, same reduction process will start happening here. So those many values got converted into single values by parallel execution on these three nodes, and followed by a kind of a reduce operation on the driver node. Okay, so that was a brief example, and this is what happens in almost all the actions. In almost all the actions, the work happens on all the nodes as well as on the driver node. Okay, so node 1, node 2, node 3 are generally called executors, and this driver node is called a driver from which things are generally launched. Any questions at this point? No questions? Now there is a question from Jitender. All right. Can a driver node be an executor too? In the proxim, in this kind of pseudo modes, right now, if you try to run Spark on your local machine, in those cases, the driver node will be an executor as well. Sounds good? Let me just save the notes. All right. So that was one example. Then we talked about folding. Folding is basically similar to reduce, just that we provide an initial value. Okay, just that we provide initial value. Then we talked about aggregate. Aggregate makes it possible to run an operation on the partitions, and then the result of partitions is given to the combination operation. Okay, so this way, instead of just having a single reduce function, we could have multiple reduce functions. Okay, now under actions, we also talked about something called count by value. And count by value, you can see that it basically does a unique minus C. You remember unique minus C from the Unix part? All right. Basically, it counts the frequency of each individual value. So you can see that if you run this particular command, it will give you 1 has occurred once, 2 has occurred once, 3 has occurred twice, and 5 has occurred thrice. Okay. This kind of statistics it will give you. All right. Next is the top, and afterwards, top is basically top actually it converts it sorts the value and then give you the values which are highest. Okay. Now, if you want to take things ordered, as in if you are exactly like the way we did in case of top, in the same manner you can do you use take ordered, and it'll give you n number of records. Okay. So the way top gives you the maximum value, take ordered gives you the minimum values. All right. If you want to use take ordered and want to get the maximum value, you can provide a function which gives a key, on which the values need to be sorted. Okay. It gives basically it gives a way of sorting the data. So here we are saying x equals to x minus 1. So sort it on the negative value. Meaning, in case of negative value, minus 10 will be the minimum and minus 1 will be the maximum, right? And therefore, it will order it in the manner 10, 9, 7, 6, 5, 4, and so on. Okay? And therefore, we will get these values. Okay, please note this function. This is very important to. Yes, Jitendra, you have raised your hand. Hi Ashish, hello Ishwar, hi Gaurav. You guys have joined a little later. All right. Now, so basically, this is what makes it. Let's just try to show you this part. Is this clear to everyone? Because I thought I had covered it in the last session. All right, I'm logging. You can log to Hadoop 3 and start using it. And I'm just logging to a different server so that we don't consume RAM on the same machine. CD Spark. All right, here we have this. This is my RDD. Okay, and if we want to take things in this manner, we can simply say RDD dot take ordered. Now you see that we got 10 first. Now, if we had to create, or let's say we create a function called x, and we want to do something different. All right, let's try to order using the string. Okay, let's just convert this number into integer. So you can see 100 has become this, and so on. Now, if you try to run that command, okay, let's say Okay, now you see that 1, 10, 2, 3, 4, 5. You remember we discussed it last time also? Do you have any questions regarding this, or is this very clear? Um, Ishwar, Mehdi, Jitender, Ashish, Gaurav, any doubts about this? Or you can suggest me a method with which I should. Good. All right, going ahead. So I was trying to display that while we have described the same thing in Lambda, we can also create a function about the same thing and then use that as instead of this Lambda. Also, please note that at no point in the whole discussion we will modify an RDD. We will just create fresh new RDDs and keep on using those. We will never modify. Okay? Now, if you want to take a sample of a number of values, we could use take sample. Let's say there is an RDD which has 10 values, okay, 0, 1, 2, 9, and we want to take samples out of it. All right. Let's say we want to take sample out of it. We can take sample like this. Now here we are saying keep on putting it back, okay, and give me 20 values out of this particular RDD. And yeah, there was one, two, three. There was a help RDD dot take sample returns the fixed. Okay, you can provide some seed. You can provide some seed. That's not really too much required. Okay. So also what I've tried to show you is at any point you can say help and the function name and you will get the listing of the function description. So you can see that it is saying take sample, ignore the self part because self means the object itself, and with replacement as in keep on replacing the element as in put it back, and how many numbers do you want, and do you want to provide a seed on which the randomization will occur. Generally in most of the algorithms, when you are computing a pseudo random number, you provide the date time or timestamp as a seed. All right. If you want just say three numbers out of it and you don't want to put it back or you don't want to provide any seed, okay, so you can see that we are getting three different numbers every time. All right, great, great. All right, so the results will be approximately those numbers. Okay, results will be approximately those numbers, and All right. Now, that was take sample. Generally, whenever we are doing some statistics computation or we are trying to do a random testing of our algorithm, we generally take sample, and on that sample we run our most of the algorithm. Okay. And generally the take sample part, as in testing on the sample, is probably the most reasonable way of testing your tool on some data. Okay. Now next is that we can also do a for each. Okay. What we can do is applies this function to all the elements of this RDD. Okay. Just like map did. But the difference with for each is the difference with for each and map is that for each brings the data to the local machine. Okay. For each brings the data to the local machine. For each is an action, while map is not an action. Map results in a new RDD, while for each doesn't. For each results in a local value. All right. So let's say we are saying print x, or we want to return the same value. We can use this. Okay. So if we are saying something like lambda x and it does nothing, okay, so it has basically given us the basically it has given I mean it has executed that function. Now inside this function, if you wanted to print, or if you wanted to just okay, if we wanted to say connect to some DB or do something, we could use it here. Okay, print, this is correct, right? Define f, and whatever value we have, we are just saying print x. And if I say 1, it just prints 1. Let's just pass this as our function. Right? You can see that it has printed. See that? All right. That was our for each. Now, in case you want to execute a function on particular partition, then you can execute the function using for each partition. So it will get an iterator of all the values in a single shot. So let's say there are two partitions. One is 1, 2, 3 and other is 4, 5. Okay. So this function for each partition will be executed twice. One for this, and this will be received as an iterator. Okay. This will be received as an iterator. Iterator is like your cursor in database, like your what do you call iterator in Java. It's a pointer to the list of values. It's referring to list of values. It just doesn't load everything into the memory. As and when you want, you can ask it for the values. So what are we trying to do here? So for each partition, we are trying to do something. What we are trying to do here is say this is the iterator. This is all the values in a partition. Okay. So for each x, in this iterator, what we are doing is we are appending plus 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 before this value. And since we cannot concatenate a string and a number straightforward, we have to use a casting function like str. And then we basically say yield none, as in we are not basically giving out anything. Instead, we are just printing things. Okay. Yielding means whenever we want to give out a list of values, okay, generally we say yield. Instead of returning, we say yield. So in yield, the overall resultant of the function would be another iterator in which the individual values are coming from the yield. Okay, so you can test it. Let's just see if it accepts an array. Yeah, so as you can see that it has given us a generator object. All right, all right. Now let's try to execute this function. You can see everywhere that it has resulted in plus 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 1, plus 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 4, 5, and so on. Okay, so it has appended the plus plus value in front of all the values in the partition. Okay, and how should let's say we put one more nice thing in this. Let's say as the partition ends, this one prints something called like this. Okay, let's see if it executes before and after the partition. All right, let's try to see. You can see that. So you can see that 1, 2, 3 are in different partition, while 4 and 5 is in a single partition. Now, even though we have not covered a function called glob, we can still just check what's happening with them. Okay, we can say glob, or what was, let's just load it as RDD. Okay, RDD dot glob glom. Okay, so yeah, just a second. All right, just let me try to do it again. So let's say we have, what do we have? We have this particular um, glom.collect. Where is the, yeah, here it shows that there are these partitions. Okay, there are these partitions in our RDD. So this RDD which we have just here, it has how many partitions? 1, 2, 3, 4, 4 partitions. Okay, and the way we computed it is by using rdd.glom, and then we said collect. Okay, so we'll cover glom briefly after some time. Also, if you want to find out how many partitions are there, you can launch you can launch okay, you can go to 4040 port on which Spark is running. All right. So let's see. Let's try to see what happened again. So these are our four. These are our four partitions, and let's try to run this function again. Okay, we'll define the function again, although it was not required, and we run. I don't know why it's not coming. Okay, we run our RDD. This is the RDD. Okay, we run this RDD in F. Now you will see, notice that 1 has come together, 2 and 3 have come together, 5 and 6 and 4. All right, 1, 2, 3, 5 and 6 and 4. Right, and the execution is not guaranteed to be very sequential. All right, so it's, I remember very well, it was this only. Definitely not anything else. So there is a question from Ishwar. Let me take that question. In the logs, where do we understand which partition it belongs to? Okay, so you mean, is there a partition number or something like that? You expect there should be some kind of a partition number and which we can print. So I don't think there is a partition number. Right? And in the logs, the way you can identify here is, you can see, what does this code say? It says that before starting F, before starting executing this function, print equal sign, and then once it ends, print this again equal sign, and before each value put plus plus. That means a function, if it is executed on multiple values, those multiple values will be between these equal values. All right, which you can see clearly here. All right, which you can see clearly, like, let me clean it up. All right, let me just clean it up. Yeah, now do you see any relation with this? So when we say glom.collect, it basically collect all the partitions together, and then we glom brings all the partitions into a single array, and then collect will bring all the element to single array. So it becomes array of arrays. Okay. So we could see from two ways that these were the partitions in our RDD. All right. There were third way of finding it out, which was through this one, and for some reason it doesn't seem to work. All right, let me just does it run for Hadoop 3? Yeah, for Hadoop 3 it is running fine. So, all right, maybe I could do with Hadoop 3 only. Actually, there is nobody, no, nothing is running on Hadoop 3. That is the reason. All right. Was he able to answer your question, Iswar? All right. So this way you can execute your function on each partition. All right. So, Ishwar, I was explaining, Ishwar's network got disconnected. So, Ishwar, I was explaining that using glom, we can quickly see how is our partition. Also, we can execute once in this logs itself, you can see that the equal sign appears before and after the function has finished executing. Okay. and and therefore you can see clearly that 2 and 3 are together, 5 and 6 are together, and 4 is different, 1 is different, which is same as what glom has given us. All right. All right, now next question is that sometimes 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 computation of an RDD is a very intensive task, and if we keep on computing again and again, it becomes a slow process, right? And again, an RDD is basically a statement. It's not a memory storage. It's a statement saying this RDD is generated by loading a file, or this RDD is resulted from transformation of another RDD. So when you say RDD.collect, it basically goes back and computes all the steps that are required to reach that particular RDD. It has to load something, it might have to run some transformation, or it has to run another kind of transformations. So so an RDD is a chain of transformations, and starting with a load. Okay. So sometimes we don't want this. We know for sure that this data is going to be used very frequently. So if we try to recompute it again and again, it will not be effective. And in those cases, we do say persist. Persist gives us another RDD which is computed. Okay. And in case the machine crashes after we have persisted, this RDD will be recomputed, and regenerated. Okay, it will be regenerated based on the previous steps. All right. So RDDs are lazily evaluated. We all know that RDDs and all its dependencies are computed on an action. We may wish to use the same RDD multiple times. To avoid recomputing, we can persist an RDD. It is equivalent of caching. If a node that has data persisted on it fails, okay, the RDD, when we say persist, it's not our usual persist. In the way we have learned persist is, persisting means taking a data, putting into hard disk. That's not here. If you are from database background, then you will notice that persistence used to be something to do with saving it in database, but here that's not the case. Okay, it's like saying this RDD does not need to be recomputed from all the dependencies again and again. That's all it says. All right. So as we can think of it, if we start thinking of RDD like a data, then we have to take care of in case this particular node fails on which we are running RDD, right? Because when we persist, it basically saves it in the memory. It keeps it in the memory so that we don't have to recompute it. All right. Sometimes, if we are too possessive about an RDD and we want to handle a failure without the slowdown, we can replicate our data on multiple nodes if we want to be able to handle node failure. Okay. So I think that answers Gaurav's question. Is RDD caching replicated? If one node fails, then it will recover or it will recompute. It will recompute. Okay. If replication is not there, the last sentence is that if we don't want recomputation, we want to keep the data on multiple nodes. All right, great. Does that sounds reasonable to you? Because recomputation is little slower process. So if you want to keep a backup, you can keep a backup. All right. Now let's take a look at our caching example. Let me fix the UI a bit. All right. Isn't it the same thing? Let's say what is it's doing here is, let's say there was this particular big array, and we are saying that we will have only 5 partitions, and then we are computing sum of each parts using map partitions, similar to what we had done earlier, the map values. Similarly, we can have the map partition. So that means there will be only 5 values at the end of it. And then we are running increase by 1. Okay. And increase by 1 is going to be run on this particular value. All right. This is not correct. Let me just fix it first. Okay. So we are saying partitions 1 equals to partition dot map increase by 1. Okay. Yeah. Now let's say this particular partition 1, is something which we need again and again. We want to run a lot of computation on partition 1. Okay. If we have to run it again and again, and we don't want to be recomputing these summations and increase by 1 again and again, then we should generally go for something called uh, persist. Okay. So what is this uh, leading to is, after we have done persist, we'll get another partition. Okay, and yeah, okay, or we can do something more. Partitions 2 equals to partitions 1 dot persist. Yeah. All right. So let's say there is a need of the last one that is computed. Okay. There's a need of the last one that is being computed. All right. I think this is okay. So here, all right. I'm hoping that this is very clear to you. First, we created an RDD called NUMS, Resilience Dataset. This data that we created is basically nothing but prepared out of this range. And what does this range? It starts from 1. It results in a big array of how many numbers? 100,000 numbers. Okay, it results in 100,000 numbers from 1 to that number, and it results in 5 partition. Okay, if we want more partition, we can add more partition. It doesn't necessarily need to be equal to number of machines. All right, so we are saying that here is our function. What it does is for each partition it will compute the sum. And when we say partition dot this, it has computed, it has basically noted it down that you want to compute the sum, and then we increase every number by 1. All right. So now when we say party, all right, again typing mistakes, partitions. All right. When we say partitions dot collect, all right, it has given us this 50 numbers. If you don't believe me, let's try to collect it in a local array, and then we say length of local array. They're giving us 50. All right. So basically, we have divided this array into 50 parts, and then did some operation, then did some another operation of increasing by 1. And let's say this partition 1, partition 1 is going to be used very frequently. Okay, very frequently. So every time we will do any operation on partition 1, we are going to go through the full chain of executions again and again. To avoid that, we can do partition 2 equals to part partition 2 equals to partition 1 dot persist. Okay. Now, once we do that, and whenever we run an operation on partition 2, it will not go through the same chain. Okay, it did went through the. Probably it is running in a low memory or something. So yeah, it's a little faster. Let's just try to notice how much time did it take. Yeah, it's saying that it has found the block locally. It took around this much seconds. Let's try to see if that's correct or not. All right. Partitions 2 took this much time. Let's say we have partition 1, and in the same manner we'll call partition 1. Alright, looks like this is also taking so much time. Alright, not much of a difference actually. Okay, okay. Also, yeah. Partition 2 per is cached. What? True is, oh, both are cached. So actually it has partitions dot is cached false. And how much time does it take? It took around, yeah. So partition 1 and partition 2 were taking approximately same time, while partition was taking this much time, and these both were cached. Okay, these both were cached, not cached. Right? So try executing all of this again. But interesting part is that when we say partition 1 dot persist, it's actually persisting both. I mean, making partition 1 and partition 2 both cached. All right. So basically, you don't require this persist is modifying the RDD and marking it as if it's a. All right. Let's just try to. So okay, this is not cached while this is cached. Yeah. So this is basically modifying. Not really. This is not modifying. Let me just try to see, because there are few things which are sometimes not clear. All right, let's just see what happens in this case. This is false. This is true. All right. Now, okay, this is clear now. Let me explain again. So what we have done here is we have, okay, so let's see what we have done here. We have taken this data of 100,000 records, put it in 5 separate partitions by marking it 5 here by using parallelize, and this is basically, you can think of it as if it's an array of arrays containing only 5 arrays, and each array is having uh, around 20,000 records. Okay, when we say, when we define a function like this, we are saying sum parts and on iterator. As in, for this whole iterator, sum up all the values and yield. Yield is equivalent of return. But in case you are giving the data to an iterator, yield is the one you have to use. Okay, specifically for using map partition, not maps. Now, when you say map partition, this some parts will be executed on each partition, and all of the values of that partitions will be passed to some parts. So for it will be executed for each partition, and on each partitions all the values will be passed to some parts as an argument. And what it will do? It will give the summation of each individual partitions. And effectively, this particular component called partitions will only have five values. Okay, it will only have five values. And when we say partitions dot map increase by one, which is this function, it will be called only on five values. And afterwards, persist one. Okay, so this particular data set, persist one, will only have five records increased by one. And when we say persist one, partition one dot persist, it will save it, and it will not do much of a recomputation. Okay. And you saw it when we did the computation. It took around 0.12 seconds, while computing partitions took 0.69 seconds. All right. And to test it whether something is cached or not, you can always use is underscore cached on the RDD. All right. Do I make sense to you now? Yeah. Ishwar, Mehdi, Jitendra, Ashish, Gaurav. All right. So it is important to actually go through all of these steps, and you should also try all of these things by yourself, each example which has been mentioned here. All right, great. Now, if you notice, we did not give any arguments to persist function. And when we do that, it basically uses the memory. Basically, it uses the memory. And there are many more options. As you see in this here, there are many more options that we can pass. All right. Okay. So let's a little bit talk about what are these persistence labels. All right. Now there is a question from Asis. Does creating many partitions will impact performance? Yes. Okay. Yes, because if it is not required to create partition, then don't create. Okay. If you have only 10, 20 machines, if you have say 10 machines, it's okay to create three times the number of machines. Okay. So if you have 10 machines, it's okay to create 30 partition. But if you create something like, if you have 10 machines and you created say thousands of partition, it doesn't make much sense. All right. Also, it is if you have say so basically number of partitions should be generally equal to number of cores you have. Thank you for asking this question. All right. So generally the way most of the people work is they count total number of CPU cores. Okay. One partition per core. Okay. And why is it so? Why is it so? Because what is your ability to perform parallel computing? Okay, you can run how many map functions parallelly? What is the ability? Okay, you can run total number of map functions equal to the total number of CPUs you have in your cluster. Okay, so therefore the map partitions should be generally equal to total number of cores you have in your network. Okay, so you basically count total number of computers in your network, and how many CPUs each one have. When I say CPUs, it also includes the cores. Okay, every CPU right now, the way things are happening is they are combining multiple CPUs together in order to give you a performance advantage. Okay, although you might have heard about, so let's take a good example. Probably this is very useful. And let's say you are writing a code like for I in range 1 to 10,000. All right, and all you are doing is process I. Okay, now this code cannot take benefit of multi-cores on your machine, no matter what you do. You will have to divide your logic into some sort of map or reduce, even on the local machine. You will have to convert this code into your map. You'll have to say map range 1 to same number, and then your function called process. This can take the benefit of multi-cores. You can tell Python, or even if you are in Java, the only reason you would create bigger threads, more threads is first, if two things can be done in parallel. Second, if you have more CPUs than required. Right? Now, more CPUs than one. If you have only one CPU, then there is no point in trying to do too much of trying to run the same piece of code multiple times. All right, so basically this is how you generally design your partitions. All right, this is non-distributed. Okay, and this is distributed. All right, coming back to our persistent discussion. So, all right, so persistence can not only be in the memory, but can also be on the disk. By default, it is in the memory. Sometimes you may want to put it on the disk, and memory only is the default option. So these are the various storage level, starting with memory only. So memory only stores RDD as a deserialized Java object in the JVM. If RDD it's not serialized, mind it. Serialized means converting the RAM into disk. It's as simple as that. Containing objects which are in the memory, and in the memory how are the objects represented? The way in the memory the objects are represented is with their address, and with the address each value can be identified quickly. And on the disk the same object has to be put down as a file, or in the cylinders of the disk. Okay, so so this translation from the object format, in memory object format, where there is a address it holds in the memory, and all the variables of the object hold some sort of address in the memory, and taking that and putting it into the disk is the process called serialization. By default it's only memory only, and it does not create any serialized object. So persisting as memory only is faster. If sometimes the RDD is not fitting into the memory, some of its parts will not be cached and will be recomputed every time. So if your memory is low, Spark will identify that. And when you try to persist really huge data, it will not persist it. Okay? It will not persist it. It will basically say that we will recompute it on the fly. All right. Now the second storage level is memory and disk. In this case, it stores RDD as deserialized Java object in the JVM. If RDD does not fit in the memory, instead of pushing it back as normal RDD, it will store the partitions. Okay. All right. This is not correct. Okay. All right. It actually like this. Okay. This there is a mis. Yeah, I think the partitions on disk that do not fit in memory. All right, I think now this makes sense. So in first case, if the partitions were not fitting into the memory, it will leave it as such and will be recomputed whenever required. But in case of memory and disk, if the partition does not fit in the memory, it will serialize them onto the disk. And in case it doesn't fit into disk, then of course it will leave it RDD as such and will 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 follow will recompute them whenever required. Now memory only serialized. Store RDD as serialized objects, Java objects, 1 byte array per partition. Okay. So basically if you mark an array as memory only serialized, you basically sometimes compress the data in the memory itself. It's more efficient to some storage wise efficient to keep the data as serialized. Okay. So it's when we are saying memory only serialized, what exactly are we doing? We are converting the whole object into some sort of a format such as a string, binary, or basically we are converting a large object into a small compact object. Okay. And there are many tools to do that. There is a fast serializer which basically convert a big object into it flattens the object and makes it a like a string or a byte array. And that's how the memory only serializer work. And every time you will read memory only serializer, it will be slower than memory only, but it will be faster than memory and disk. Okay. So it's a trade-off between the disk space and time. All right. There's a question from Gaurav. It says that RDD as well as RDD cache object use memory. It means that we should have large RAM for Spark application. That is true. Um, so so there are multiple modes. Okay. So how should I explain? Let me take a step back. So only RDD cached object take memory. Okay. Generally, RDDs do not take memory. When we say RDD equals to sc.parallelize, it has not really converted it right away, or it has not brought everything right away. We'll do it later. It has just mapped the partition to various storage. But in general, Spark do consume more memory than MapReduce. Okay, the usual Hadoop MapReduce we are talking about here. Now, next question from Iswar is, how much space efficient could it be? It won't be too much actually. As per my understanding, it is around 20% compact. Okay, it's around 20% compact. I need to look at exact numbers. We'll try to compact and then see a large object, and then it'll give us an idea. All right. Also, it also depends on structure. You can imagine that if there is an object which only contains single string variable, then if you try to compact it, it wouldn't serialize it, it would not make much of a difference. All right. Next point is, now there are other modes of persistence, not only this. We talked about three so far. One is memory only, where data is only in the memory. Then memory and disk, where extra data is pushed to the disk. Then memory only serializer, as in it is memory only, but it is the data gets converted into serialized format. Okay, if you have little less frequently used data but too much data, then memory only serialized Java object will be good. Specifically, if you are trying to use Spark for huge objects, then and you want to keep it in memory, then memory only serialization is good. Okay, it's like saying that if you compress the data, what is the benefit? The benefit is storage, but if you compress the data, every time you decompress, it is going to take time. All right, good. Now, fourth level of serialization is memory and disk serialization. Okay, so it is similar to memory only serializer, but it spills the partitions that do not fit into the disk instead of recomputing them on the fly. So it's memory only serialization and disk. Okay, just like memory only and memory and disk was there, where part which was not fitting in memory, it is being pushed to the disk. Now in this case here, by default the data is stored in the serializer format. Okay, and if it's not fitting, if it is not fitting, it will push them to the disk. Now disk only, it saves the data onto the disk alone. All right, if your data is really huge and you know that it won't be required too often, you will push it to the disk only. Now if you want to keep two copies of memory only, you can say memory only underscore 2, same as above, but it will keep 2 as the status. And if you want to three copies, you can put 3 here. Okay, it's as simple as that. If you want memory and disk and want to keep 2, basically you can suffix a number after all of these modes, okay, to mention that these many replica factor you want. All right. After any of these, you can put underscore and a number, and those many copies will be created. All right. Of the heap is experimental, and it generally stored RDD in serialized format in Tachyon. It's very experimental and is new. All right. But for us, these four modes actually are very important. Five modes. Okay. And rest are derivatives. So memory and disk, memory only serialized and disk, and serialized, and disk only, and then if you can put disk only underscore 2, it will keep the two replication partition in your cluster on two different nodes. Okay. Now the way you call it is in two methods. In Python, when you are calling this, there are two ways to call this. Okay. You first define an storage label. Okay. You first define an storage label like this. Okay. uh, Let me just try to create a storage label, and then after that you can say partition 1 dot persist, and then pass the storage label which you just created. Okay. So it says that cannot change the storage label of an RDD which is already assigned a label. Okay. You can say unpersist, or we can just create another one, persist. Okay, so it has removing RDD10 from persistent list, and then but then if you say it has again persisted it. Let's see what has it actually done is cached. Yeah. All right. So what we have said here is there are two ways. In case of Python, you can pass arguments in two manners. Okay. One is we call keyworded arguments. We mentioned that we mention in the form of key and value. We are saying use disk true, use memory true, use heap false, and replication true. Okay. Internally, it is going to set any of these ones. Okay. So this API is far more cleaner than these flags. So if you want to keep disk is true, use memory true, use off the heap false, deserialize true. So basically, based on that, you can use you will be using internally any of these flags, the storage labels, or you could simply say true in the same order. Use disk true, use memory true, use off heap false, and reserialize true, and replication one. All right. And what exactly is off heap? All right. Have to look at what is off heap. All right. We'll uh, we'll discuss it later. Right. So because this off heap is a flag introduced in Python API which is not there yet. Let me see if it is mentioned here. Help rdd dot storage label. Yeah, says that it built in this. All right, it says 1, 2, 3. Almost for everything. All right, we need to see this off heap label. It seems to have introduced lately. Okay. So heap is generally the memory where you are keeping your objects. Okay. While stack is a memory where the function declarations are kept in the memory. So we'll think about it again. All right. If you want to see the detailed API in Python, you can simply go to the Python API here. It gives you in detail. This is the latest version, which is 1.5.1, and you can have details. Okay. And if you want to see, let's say, what is the storage level of something, you can simply say get storage level. So it shows you that this is the storage level, right? Okay, so you can go through this API. This is like more detailed, and yeah. All right. So Iswar is asking for a break. Yeah, let's take a break. All right. Yes. Um, break for 10 minutes. Back by 8:47. Yeah. Sorry, it is 8:37. All right, it's 8:37. All right, so I'm back. Should we start now? All right, Mehdi is back. All right, Gaurav is back. All right, nobody else is back. Ashish is also back. All right, Jitendra is back. All right, let's start then. Only Iswar is yet to join us. All right, now there are a few questions which I want to answer here. All right, does caching uses whatever memory dedicated to JVM, or will it the consume system memory completely? No, it won't go beyond JVM. Okay, so those of you who are wondering why is it so, at the end of day, the executor executor and driver both run inside JVM. Okay, so both run inside JVM. All right, and in case a driver or executor try to reserve more memory than available in JVM, there will be a memory overflow, and that particular instance will be killed by JVM, and it will no longer we'll no longer be able to execute the executor or the driver if they are consuming more memory than required. Okay, now so sometimes the here when we say persist, it's also persisting to the disk. Okay, so yeah. All right, all right, so Ishwar is back now. Good. JVM is Java Virtual Machine. So that was up to our basic discussion of various operations on RDD. Along with that, we talked about persistence. The we talked about uh, what else did we talk about? Yeah, we talked about various function parsing in this class. We talked about the basic operations and various steps involved in translating data from one form to another. Okay. Also, we talked about how to submit a job and how to get things done. So this was probably the most important session for Spark, because in this one we learned how to start Spark and how to get up and running. Now you will be surprised to know that almost all of the things, machine learning and everything which has been built on top of Spark, has been built using these actions and transformations. Under the hood, everything is an action or transformation being applied on an RDD. Okay, be it recommendation engine, be it various kinds of machine learning patterns, everything is built using transformation and actions. All right. Even Spark R, the whole thing is written in using this, using uh, Spark RDD actions and transformations. Sounds good? All right, moving on. So this was what session it was? Yeah, it was concept session. Now let's go ahead with the. All right. So far we talked about our RDD as if it's an array of values. Okay. Now, if it's an array of values, there are many operations that cannot be performed so easily. But but in RDD, RDD is basically an array of objects. Now, what form is this object? Right now, so far, whatever we discussed, we only tackled as if each individual object is very primitive type, number or a string. But each individual object could be a complex object, could be a very complex object in the sense that we could keep various kinds of things in the object. The whole customer object could become one particular element in case of RDD. Or the whole RDD might represent a single customer where each element represents the past history of that customer. Okay? So basically, an RDD can always be visualized as an array list of object. An object could be anything. Object could be an object of objects, or object could be further an array. Object could be a kind of a key value pairs, where key and value both could be complex, and no, only value could be complex, and or object could be as simple as a string, right? So now, when you have to do many operation, so such as doing the word count, such as doing various kinds of statistics or machine learning work, people found that they are very frequently working on something like a key value objects, where each individual object was in the form of key and the value, name and the value. So and they realize that most of the time they are working on various kinds of operations which fit well together with key value. Say for example, you are joining two data sets, you are doing union, you are doing group by. In all of those, there is always a column such as ID column, okay, which is the key, based on which we are trying to identify each object, right? And that's where the idea of key value kind of RDD came into play. So key value pairs RDD is nothing but a normal RDD where each element is in the form of key value. Okay. And a pair in Python is defined at xy. If you want, I can take a quick look at what does a pair looks like. Okay. So a pair or tuple is looks like this. All right. Looks like this. It might look to you like an array. Okay. It might look to you like an array. So let's see how does it look. There is 2, 3, and there is 2, comma 3. Both look same to you, right? X0 is 2, Y1 is 3. You can see that. Okay. So X into 2, Y into 2. You can see the behavior of both array and tuple looks very same. Okay. And yeah, you could keep the same value as well. Now your question is what is the difference between array, which is square brackets. You can see the square brackets. Yeah. And here it's round bracket. This is tuple. Okay. And this is how we will deal with key value pairs. All right. So you can see that these tuples and array look very similar, but tuples are essentially ordered pair of collection, and tuples are tuples have a little different dynamics than the array. All right. But in our case, we will be talking tuples. And when in function, let's say there is a function called define f, and what it returns is things like return 1 comma 2. Okay. And when we call f, it returns us a tuple. Now, the difference between tuple and array or a list is the biggest difference. Tuple is immutable. Tuple is immutable. If we want to say x dot append, and what is x? X is a list. X dot append, and we say 3. Okay, so you can see x has been appended to 2 comma 3. 3 has been appended to 2 comma 3, and if we try to append, we cannot append anything to y. Okay, there is no such thing called append. But to y, we can add another tuple, something like this. Okay, something like this. But if you have single element tuple, you represent it like 1 comma. At least a comma has to be there. So y1 equals to this, y is this. So you can see that. But you cannot have, you cannot alter an existing tuple. That makes it a very good thing for passing values in functions, so that the function does not modify your tuple. You remember when we had, if you guys have been from Java kind of background, and whenever we had to pass, let's say my function is there which need coordinates x and y. So we used to create a class called rectangular coordinates, in which there was one thing called x and another thing was y. So we used to remove the setter from it. There were only get x and there were only get y. Okay. And in this, there used to be a constructor. There used to be a constructor x comma y. So this was a common design pattern, and this was very much required when we want to pass something which we do not want to be modified. We generally used to create our immutable class. The way our string class is designed, anywhere in any language, the way string class is designed, it is immutable. You don't modify an existing string, instead you create a new string. So that is the biggest difference between tuple and array. In case of array, you can modify an object. Here, in case of tuple, you don't. Okay, let's have a look. So you have got y and you have got x. X0 equals to 10. And now you can see that it has been modified. If y0 equals to 10, it gives an error. It does not support item assignments. All right. So therefore, since our RDDs are immutable, the elements, it made sense to keep RDD key value pairs in the form of tuple. All right. So let's have a look at what does a RDD with tuple looks like. So let's make an array where 1 is 1. Okay. So and 2 is 2. All right. So you can see that we have created an RDD with two objects, okay, 1 and 2. These are the two tuples which we have created. All right. Now no tuple will be partitioned. Okay, it will always be available as a whole to you. So if we want to parallelize it, let's say RDD equals to SC dot parallelize. That means we are converting our array into an RDD. Now, if you want to do say map, okay, define our my map function. What it gets is a tuple in the arguments. All right, and let's say it is trying to switch the tuple. It can create another tuple like this. All right, we are switching the tuple values in this. Let's say rdd1 equals to rdd dot map and my map. Sounds good. Now if I say rdd1 dot collect, all right, so you can see that the position of 1 and 2 had changed. All right, so when we talk about key value RDDs, the first one is the key and second one is the value. All right, first one is the key and the second one is the value. All right, and in this case, okay, in this case it is the numeric 1 and numeric 2 is the key, while in the second one it is alphabetic 1 and alphabetic 2 that is the key. Sounds good to you? This is how the pair or the tuple is defined in key value in Python. Okay, although it's very simple to create a list out of, sorry, so let's just try to do something. All right, I think you can create tuple from an array. Yeah, and you can create array out of tuple. Can see that? So you can translate back and forth between tuple and list at any point of time. All right. So key value pair RDD is nothing but an array of tuples where tuple contains at least one key, which is 0th element of a tuple is considered the key. All right. Now, the first thing we want to do is we want to convert a text into our key value tuple. All right. Let's say there is this sentence called "This is a bird." Okay. We will also talk about how to. So this is a string. If we split it in Python, it becomes an array of one word. Okay, array of words. So let's call it A, and let's say we want to convert it into RDD. So what will we do? RDD equals to, quickly, we want to convert this A into an RDD. What will we do? Yes, I'm asking all of you. All right. So Gaurav, it will be SC dot parallelize. All right. If we say A dot parallelize, it will give an error. All right. So now we have got an RDD. Good, good. Thank you, Ishwar. Thank you, Gaurav. Now, the moment we say, now let's say this is our RDD, and let's see what is inside it. So it shows us that it is basically a big array of elements. Now we want to convert this into each word followed by a number, something like this. Okay, you help me out. All right, something like this. We want to convert it into something like this, such that our key becomes in the key value kind of model. Okay, the word is our key. Something like this. What should we do? Anyone? We want to convert our this into this. Yes? Yes? So we have to convert our RDD, which is in this format. You can see this is a bird into an array of tuples. What will we do? Anyone? Yes, Gaurav, Ishwar, Jitender, Ashish, Mehdi. So both are our RDD, this as well as this. All right. Um. Yep. No answers. Should I answer, or are you typing? All right. So we want to convert our RDD, which is of this form, into. We want to convert this into something of this sort. We are trying to form a key value kind of RDD where each element, instead of being an atom or instead of being a primitive type, it becomes something like a tuple which has at least one element, because first element is considered the key. Okay, so what do we do generally? This is our RDD, and this is, I think, our RDD1. Let's just try to see. Yeah, so that's our RDD. So what we'll do, RDD1 equals to RDD1 equals to RDD, or let's just define a function f, which takes a single element and returns. Yes, thank you, Gaurav. On the same line. Yeah, the only problem with for each is that it will bring the data back to the node. Okay, instead we will use map. Okay, so we are returning this. So we can test whether it's working or not. Yes, it's working fine. and we can say rdd dot map and f. rdd1, let's assign it to. Now rdd1 dot collect. You can see that it has converted that into this way. All right, is everyone with me? So we've successfully converted it into key value pairs. All right. So two key value words. Okay, let's call it words, not lines. All right. Now next is so there are many operations. There are many operations on key value pairs, as you will see now. There are many operations on key value which are very useful for any computation. All right. So we'll see what all operations are there, because those need to be covered, and we need to understand what all is possible before we, because we'll have to, at the end of the day, we'll have to convert our existing computation into an RDD. So we'll have to figure out what is the best way to do it. Okay, as we will see later that at least there are 3 to 4 ways to do the word count. Okay, we'll explore those also. All right. So I mean, rather than memorizing, it's important to understand how does each one function. So first one is keys. Let's say there is in here, if we just want to get all the keys. Okay, so this is the RDD which contains only the keys. We have to say collect. Now you can see that it has brought only the words back. Okay, sounds good to you? Or you can try this as well if you are in mood to. So m equals to sc dot parallelize, and we said this is 1 2 3 4, and then we say m dot collect. See, it has collected 1 and 3. Sounds good? So these are operations specific to transformations. Glom is not really with respect to the key value pairs. Okay, glom is a general function which we had missed earlier, but it seems important, so I've included it again. Glom basically convert convert all the elements inside a partition into an array, and then gives you an array back. Basically it converts the whole, it converts your RDD into array of arrays. Okay, you can see that. So yeah, although sorted is not really required here, what is required is rdd.glom and then collect. Glom is a transformation which basically brings all the, it converted it into 1 comma 2 and comma 3 comma 4. Okay, what happened to my, yeah, let me just see why it's not giving me results. Am I doing something wrong? Which node am I on? Yeah, I'm on student. No, it is saying this. Looks like it is blocking this. Okay. Yeah, here it is. Okay. So there is nothing right now, and let's try to do. For some reason, it's not showing me. Anyway, we'll see to that later. Generally, it shows you these objects here only. Never mind. Yeah, let's continue. All right. Now, this sorted is Python's function, the local one. After it has collected all the data, it has again sorted it. It's not really much required. All right. Let's avoid the confusion. Good. Next is on key value pair transformations, we can call something like values, and it will give us only the values. Just similar to keys, where it gave you only the keys, it can give you the values as well. Okay, so you can simply try, and you can say rdd dot values, and it will give you all the values, and can say collect. These are transformations on an rdd. Okay. All right. What is happening? All right, so when I say collect, it will give us 2 and 4. Okay, you can see that it has given us 2 and 4. So we can get the keys, we can get the values, and if you want to run only the values, okay, for each of the pair through a function, through a map function, then we can use map values. For example, here, if we just want to increase the value by 1, then we can use something of this sort. Okay, we can use something of this sort. Okay, so let's have a look. So here we are defining a lambda function, which basically takes the value x, that is the argument to the function, and we are returning this value. Now let's collect it. And when we collect, you see that the values have been increased by 1. Sounds good? All right. So the other one is flat map values. Okay. If you want to just increase it, if you want to just do a flat map on values, flat map, what did it do? Just like map and flat map, here is map values, flat map values. When one value is resulting in multiple values, it makes sense to use flat map values. Okay, so for example, let's say right now each of our RDD object is a complex object of key and the values. Now let's say we want to convert it into AX, AY, AZ. Okay, AX, AY, and AZ. Just opposite of what grouping does. Okay, this is not correct. All right, this is correct actually. Yeah. So what does it do? It basically returns the element as such. And you remember our flat map? Flat map was supposed to return an array of value, and those array will be considered as separate values. Okay, and that's what we did here. All right. So you can see that the elements have become separate object. Earlier there were only two objects in our input data. There were only two objects. Okay, there was one object and there was second object. All right, and we converted into how many? 1, 2, 3, 4, 5 objects. Sounds good. So you can see that flat map is more like ungrouping the data. If we had to group this data, we will have to we will have, if we group this data by the key, X, Y, Z will come together. Similarly, P and R will come together, right? So flat map values is more like opposite of that. And of course, it all depends on our function. What does it return? Sounds good to you? All right. After this, after these two, three more ideas, we will get into hands-on exercise where all of you will have to participate. All right. All of you have to participate in that. Okay. Let's now reduce by key is another transformation. Note that it's a transformation. What does it do? It basically brings all the values for a key together and then reduces those values into one. Okay, so for example 1, 2, 3, 4, and 3, 6. When we say reduce by key, okay, first it will group the values by their key, which means it will be converted into, so let me, when we reduce it by key, this will get converted into this. Okay, 1, 2, and 3 comma 4, and like this. All right, so 4 and 6 have come together. Now this will be reduced, and on what basis? Based on the function we provide to reduce by key. Okay, so let's get down and try this. So we are saying RDD equals to SC dot parallelize. Okay, these are our values. All right, and next is we want to basically reduce these values for key. Okay, let's define our function x comma y, and if you remember, all it has to do is it has to return, let's say return sum of x comma y. So it's working fine. What happened? Yeah, this is fine. Now let's try to execute this. Let's try to our RDD, right? Our RDD, what does it have? Let's check. Yeah. Now on RDD, we'll say reduce by key, and we will pass this. Okay. And then we have to collect the values. You can see that 1, 2, 3, and 10. 1, 2 is fine because there is no other tuple containing 1 as the key. But 3 and this, here 4 and 6 have been summed up into 10. Sounds good? Sounds good to you? So you can see here there is another example where we have key as panda pink pirate panda pink. Okay, and when we map the things and map the things, map the values such that the values is converted into comma. Okay, now we can further do a summation by grouping reducing by key. So panda, for panda 1 and 1, if you sum it up it becomes this, and so on. All right, so basically the reduce by key is your group by function from databases. The only difference is here the key is fixed. The key is fixed. Key is the first value. All right. Key is the first value of the tuple. If you want something else to become the key, you have to run a map function to convert the key. Okay. You'll have to run the map function to switch the key the way we switched the numeric one and alphabetic one just now, in the same way. Sounds good? All right. So this one we have already done once. Okay. So we basically used map to convert this. We did the transformation. Probably this example would give you a very thought clarity on how to convert a word into a tuple. Okay. So hi, how are you? This is your initial RDD, and our function called tuple will be called on each of these values such that each element would become a tuple. Okay, each element has become a tuple. And how did it become? Because the two tuple does the same thing. It takes a word and converts a tuple. All right, so there was a big RDD, there was a big resilience distributed data set, okay, on which there were each word was an element of the RDD, and against which we ran a map, and that map executed our two tuple function, which converted hi into hi comma 1, or one value into a tuple. Sounds good to you? This example is clear to you, everyone? Great. It's clear to Gaurav, it's clear to Mehdi, Ishwar, Jitender, Ashish. Not clear? It's a basic example which we had already covered. If you have any question, I can explain again. All right. Great, great. So it's clear to everyone. Now moving ahead. All right. So if we say RDD equals to SC dot parallelize A comma 1, B comma 1, A comma 10, and We are defining a function f(x,y). If x is greater than y, it returns x, otherwise it returns y. Now question to all of you is, if we say rdd dot reduce by key and put the function and say collect, what would happen? Anyone? What will be the result? You don't try to run it right now. Alright? Try to go through this code quickly. Anyone? A1, B1, A10, and this is our function. Function seems to return the maximum of the two. Okay, so what will be the result? Alright, alright. And Ishwar, will that be enclosed in an array? Your result? Good. Yes, that is correct. So the answer will be A10 and B1. I'm just wondering where did my... Okay, okay, we are there. Brilliant, brilliant. All right, is it clear to everyone how it reached here? Is this answer clear? If not, I can explain, no worries, all right? Mehndi, Jitender, Ashish, I can explain it if you want. Great, great. So Gaurav got it. Ishwar is okay, and Gaurav is also. And Mehndi, Ashish, and Jitender. All right. Now there is a bigger exercise. Let's say I'm just trying to take this file. All right. Let's just start with a good exercise. The question to all of you is, find the word frequency of this HDFS file. Okay? Is everyone with me? All right. It will be more involved than you are used to. So okay. So first is we have to find the frequency of this particular file. Word frequencies, meaning how many times each distinct word has occurred. All right. Okay. So our first step is loading the file into RDD. Yes. So lines equals to, can somebody help me quickly? Can somebody help me quickly? All right. We can use text file. And what this text file does is it converts the whole file into an RDD such that each line in this RDD will be will be uh, will be from the file. Okay. So each element of the RDD will be a line. Okay. So we say sc.text file. All right. So sc.text file. Sounds good. Now second step is to peek into it. How to peek into it? How to look into what's there in peek into lines RDD? This is an RDD. Let me just put it in the variable name itself. Okay. All right. Let me ping the URL. All right. Let me give you the full this one. Okay. Did all of you got it? Good. Thank you, Ishwar. All right. So how to peek into it? Anybody? Lines RDD dot. Yes. We just have to take, say, first few lines. So what do? We say take, and let's see what is there in this RDD. Okay. This is take 10. All right. It's actually lines here. Let it be lines. We'll talk about it later. All right. Now you can see something here. From here to here is our data. All right. You can also go into Hue and look at this file. All right. Let's have a look at the file in the Hue as well. All right. Let's have a look at the file in Hue. And this is basically an HDFS file. So here, this is the file which we are churning, and it says the Project Gutenberg ebook of Sherlock Holmes. And the same thing is here. The Project Gutenberg, you can see. See that? So each line has been converted into an element in RDD. This is one line, this is one element, this is one element, and so on. Okay? And this line is empty. You see the object is empty. Correct. Let's do take 10. Good. Thank you, Gaurav. Now next step is we did take 10. Next step is what do you suggest? I'm just changing back the name to. Yeah. Now what do we want to do? We want to do the word count. We want to do the frequencies. For that, we will be using reduce by key. Okay. Reduce by key requires that our tuple, each word will be based on each key will be a word and the value will be 1. Okay. So we'll do the reduce by key, and there are multiple ways. We can also think of other ways to do the reduce by key, and instead of reduce by key, but right now we'll just try to use reduce by key. Okay. For that, instead of each line being the element, we need each word to be one element of the uh, one element of this thing. All right. So first of all, let's convert our RDD. Okay. Instead of line 1 comma line 2 etc, we want to translate it into word 1, word 2, and so on. Okay. Anybody, any suggestions quickly? And also all of you please note that this is an exercise which all of you must perform by yourself. Okay. This is an exercise which all of you must perform by yourself after the session. Okay. Let's define. So when do we do that? So each line will result in multiple words, right? And when such kind of scenario occurs, when one element is resulting in multiple elements, what do? You use flat map. Okay, so you define a function called flat map function. What will it do? It will be given a line, and it will return an array of words, right? Because any function which is passed to flat map should return an array of things, and it should take a single thing or single object and takes multiple objects. All right, now let's say lines dot flat map, and then we say fm. Sounds good? Sounds good. Let's first test our fm. This is great. Is it being converted into array? Yes. That means it is eligible for giving to flat map. Now it has led to another, okay? Let's call it raw words, okay? Raw words. So raw words RDD is this one. All right, let's peek into raw words. What is there? Let's take 10 out of it. You can see U means in case of Python, if you are wondering what is U means Unicode. All right, that's a common representation. All right, this is how it looks like. This is how it looks like. All right, sounds good. So we are successfully able to convert this. Now let's try to do few cleaning. First cleaning is, okay, first cleaning is remove special characters. How would we do it? We'll define what? Yes, Gaurav, Ishwar, Ashish, Mehndi, be with me. Help me out with this. Define. We are cleaning each word. Cleaning means let's remove special characters, or you can say non-alphanumeric. Replace non-alphanumeric with space. Okay, ideally we should have done the cleaning before, okay, and then split. Let's do the cleaning before. Okay, we'll do the cleaning before and do the flat map again. Okay, how do you clean? Let's say clean lines. Clean line. You're given a line, and what will you do? You will replace. Okay, so let me just try. I think uh, this. All right, I think we'll do the cleaning in the second go. Right now, let's do this cleaning. Anybody has replied? No. Cleaning as in convert it into to uppercase, convert to uppercase. Okay. So how do you do the upper? You'll just say the or lower. Okay. Let's just convert it into lowercase. We want to clean the data, so we'll define our function called toLower, and given a word we will return word dot lower and return. Okay, and we say lowercase words equals to raw words dot map. Okay, now remember that map function is being applied on a one word at a time, because our after flat map, our RDD contains RDD is made up of words, not lines. Okay, So we can say things like this, and everything becomes a lowercase. All right, so it is a lowercase now. Let's test. Lowercase, is it working fine? Yes, it is working fine. Yes, it's perfectly working fine. Now let's do lc word equals to raw words dot map. Now this is our. Now there were one thing we wanted to do is remove empty lines. Okay, or remove empty words. There are some words which are empty, which are empty because either there were double space or there were nothing in the line. For example, these lines, you see, these will be empty words. If you say lc word dot take 10, at least one word will be empty. The project, not this one, say take 50. So you can see here the project Gutenberg, this, and do you see any empty line? All right, there would be definitely there would be empty lines. Although I can't locate one. All right, never mind. So we'll just try to do. If I have to do the empty line, I just have to find it. I'll just come do the map and compute the length and then do the sorting. All right. Now let's try to remove the empty words, as in words with length 0. Okay. And also let's do the count. lc.count is this many. Okay. This many. Now let's remove the empty words. How would you remove the empty words? Anybody? Give me a hint. How would you remove the empty words? Just give me a hint. There is an RDD out of which we want to remove certain elements. How would you remove certain elements? Or is there a way to prepare a new RDD and put only some, not all, only some elements? Yes? Correct. Thank you. Thank you, Gaurav. It is. We'll do the filter. We will say lc word dot filter, and our criteria is lambda. Lambda is our anonymous function. This is our word. Length of word should be greater than 0. Okay. Okay, length of word should be greater than 0. So it is returning false, and this is returning true. Perfect. Now we will use this non-empty local non-empty lc words. Okay, we'll use this. Done. Let's see it is okay or not, and say collect. Okay, not collect. Collect will be too much. Let's try say take 20. All right, it's working fine so far. Now next, this is fine. Now we have got an array of words. Now there are multiple things which we could do at this point of time. One is we can say what was that? We This was the previous session, right? All right, we could do was there an empty length? Did you see empty length? So we have removed the empty length. Okay, now, yeah, we were talking about one function which did the statistics for us before the last one. Not this, not this, yes, not this. This was count by value. Okay, so we could also do count by value and get the numbers. Let's try to get the numbers using count the value. Let's see if it works. Okay, you can see it has returned, it has given us count by value. Okay, so one is we can use right now count by value, or this is 6a, and the other technique is to first, other is reduce by key. Okay, other is reduced by key, because count by value will be very inefficient. Okay, count by value will be inefficient. We'll talk about it why. So let's try to use reduce by key. For this we'll have to convert our text into key and value. And how do you convert key to key and value? Is the way we did earlier. To key value, say this is our word, and it would return word comma 1. All right, now we'll say key value word equals to this dot map and to key value. All right, all right, now let's say key value word and say take 20. You can see it has formed the tuples. And then reduce by key. And how do you do reduce by key? Counts equals to dot reduce by key. And for this we need to pass a function which will basically do summation of two values. Okay, summation of two values like this. All right, now counts dot take 10. You can see that it has done the job. Let's try to run it. Counts dot collect, counts dot collect. So it has started giving us the results. You can see that it has done the counting for us. Sounds good to you? All right. There's another function called group by key. We could also use that one. First group it and then do the reduce. Okay. The same approach is also mentioned here. The same approach, what we had just discussed. All right. Is everybody clear on the word count? So please make sure that you run this whole program or code it by hand from the beginning till end. Okay. All right. Make sure that you code it by hand. This will be available in the LMS. All right. Now you could also use something like group by key, whereby in the function called in the function all the values for a group will be passed through your function. Okay, so let me just explain what does it mean. So group by key basically groups these things together. It doesn't do anything. It doesn't accumulate. It doesn't run any sort of aggregation. Okay. While reduce by key did two things. It did a grouping and did the reduce. So therefore, but in case of group by key, it only collects. Now you can guess it correctly that when you group these values together, it is going to overload your elements to, I mean, it will overload the values. Okay. And when we run this, when we do the collect and when try to run this whole thing is running on a single machine. It's not running on multiple machines. You get my point? Because what we have done, we have said collect, and then we have said for I in wells, print this, print that. So we are going through the whole list of things on a single computer. While in the reduce by key, the summation was being executed parallelly on all the nodes. Summation was being executed parallelly on all the nodes in this in the network. Okay? So if we had to do the group by key here, so we have these nice words. Let's say this one. Okay. Let's say we had these words, not empty lowercase words. Okay. If we do this dot group by key or not this, we have to first form the keyword key. Okay, this one. Okay, instead of this step, the seventh step. Okay, what we are doing here is another 7a step, which is group by key. Okay, group by key means all the words will be grouped together, and here what will happen is then we'll have to either do the map values. Okay, map values and pass our sum function. We could also do things like this. Okay, pass our sum function, and this is mapped values and map values dot collect. What does it say? Sum takes, oh, okay, that's correct, because here all the values of all the values will be given together. So we'll have to define our another function which takes iterator. Okay, and in this it, what it does is it starts with say v equals 0, and for I in itr v plus equals to I, and then it return v. Okay, because our function sum function only takes two values, while here we are required to pass more values. Okay, Oh, sorry, again. We made a mistake again. And yeah, you can see that we have got the answer this time as well. All right. All right. So this was our second approach, third approach actually. We could also use group that the other method, count by values. All right. Sounds good to you? The only downside is that this is too much of work. This is too much of work being delegated to one machine, right? Imagine that if 50% of the values are being grouped together, then all these 50% values will be aggregated on a single node. And that single node will be bothered, will be first, there will be a shuffling effort. The moment you say group by, there will be a shuffling effort. If you don't have combiner, I mean, if you remember in case of MapReduce, if we do not have combiner, there will be too much of traffic, right? Here in same is the case here. In case of reduce by key, at every step, whenever it encounters two values for a key, it quickly reduces it, okay, using your function, thereby reducing total amount of data that is being transferred across the cluster. And therefore, reduce by key will be far more efficient than group by key. Sounds good to you? But sometimes you want to group all the keys together. You cannot avoid that. In those cases, you can use group by key. Is everyone with me? The difference between group by key and reduce by key? If let's say, if we had to, do something where we needed all the elements, let's say we had to compute average of all the values, okay, because not every function is suitable for reduce. You remember our property we discussed, because reduce is being applied again and again. If you want to compute something like average, or say some other value, say mean deviation, which is not appropriate for reduce function, you will use group by key in those circumstances. But keep in mind that group by key would transfer the data from all the nodes for a key to a single node, and therefore it is like your reduce, it's like your map reduce from Hadoop, okay, reduce from Hadoop's map reduce, and Hadoop's map MR. Group by key is like that because it brings all the values together to a single node. If you have, even if you have multiple reducers, Hadoop map reduce brings all the values for key together to a single node, thereby it impacts the node. But in case of reduce by key, at every step it keeps on minimizing the data. The moment it encounters two values for a key, it runs through your reduce function and reduces those two values into a single key. All right, good, good. So keep that difference in mind whenever you think about these alternatives. All right, so who can tell me what will be the answer of this one? Yes, anyone? Okay, good, Mehdi, good. I'll not tell the answer yet. Yes, quickly. Ishwar and Gaurav, Ashish, Jitender. Mm-hmm. Are you sure, Ashish? Look at it closely. Look at it closely. So what we are doing is, in first pass, we are grouping it by the key. And what is the key here? And then whatever values are there for each of the value for each of the group, we are saying map values. For each of the element which is the group, we are running the map function called length for each of the group, and then we are collecting together. Quickly, Gaurav, Ishwar. Now, all right, correct, correct, good, good, Gaurav, good. Jitender, yes, I think you are correct. But you need to give me the complete answer. All right, the answer will be A is 2 and B is 1. Everybody okay with this answer? Yes? Are you okay with this answer or should I explain? Should I show you stepwise? I could show you stepwise these answers. Yeah? Is it either you are clear or you I can explain again. All right? Are you clear? Gaurav is clear, Jitender is clear, Iswar is clear, Mehndi is of course clear because he has given the answer, Gaurav has given the answer. All right? All right? All right. Ashish, are you clear? What happened here? Why you got it wrong in the first shot? No? All right. So let me try to explain. Yeah, here. So when we say RDD equals to this, okay, and I say RDD dot collect, let's see what is there. Correct? This is up to here. Everybody should be okay. Now let's try to do it in parts. RDD1 equals to this. So if I say RDD1 dot collect, what is there inside it? Inside it, you will see that these are the groups. These are the iterators. Okay, each of the iterator is nothing but a nothing but a nothing but a group of values for that key. Next, map values. I want to try one more thing. RDD1 equals to RDD dot. Okay, RDD1 is RDD dot group by. RDD2 is RDD1 dot map. I want to convert this. I want to try this. RDD2 dot collect. Not this map values. You can see that what has happened here. So basically, when I say list basically converts the group of values into array, iterator into an array. You can see this is what is done by group by. Do you see that what has happened? And now if I run length on each of this, if I run length on each of this, what will happen is it will become 2, it'll become 1. Okay? So if I run length on each group, see that? Ashish, is it okay now? So this thing we converted it into, all right. Let me try to. This got converted into, where is that answer? Yeah, this here. All right. So group by converted this into this. Sounds good. All right. Group by converted this, and then when we run length on each of this, it would become this. All right. Good. Great. All right, then we will continue our discussion further operations on pair RDD and then how to load the data into Spark tomorrow. Okay, see you tomorrow. Have a great day ahead. Bye bye.